Welcome to the NPTEL online course on Fractals and Multifractals. In the last class, we have discussed the construction of proper iterated function system to generate the fractal interpolation functions. So, in this class, we are going to discuss what is the fixed point of the iterated function systems. So, in the last class, we for a given set of data points, we have constructed the mapping Li of x and Fi of x, where this Li of x controls the given data point in the x direction, this Fi of x controls the given data point in the y directions. We have taken this Li particularly as the contractive homeomorphism, this Fi is contraction with respect to the second variable. Then we defined this mapping Wi as the combination of Li of x and Fi functions. So, this is contraction mapping and Fi is the contraction in the second variable. Then we obtained that Wi is a contraction mapping. Then we have formed the iterated function system f like this one. Then the self mapping f from h of x to h of x is defined by f of b equal to union of Wi of b for all b belongs to h of x, where this x is the I cross a comma b closed interval a comma b, where I is the x1 to xn and a is the minimum of yi we need to take and maximum of y we need to take. Then take the maximum, all the maximum point, that is b, minimum among all the minimum point, that is we can call it as a. That means the given data set xi and yi, we can form the interval I and we can form the interval a comma b and take the Cartesian product. Both are the compact set, in particularly complete space, therefore x becomes the complete space. Then what is h of x? H of x is non-empty compact subsets of x. All possible non-empty compact subsets of x we can denote it as h of x. It is the hyperface of x. In the IFS theory, we proved that h of x is a complete metric space whenever x is a complete. Here x is a complete metric space, therefore this h of x is the complete metric space. Now we defined the mapping f, that means the Hutchinson-Bansley mapping on h of x by using wi's. Then this mapping f has a unique compact invariant set. That set we can call it as g of g, such that compact invariant set means it will satisfying this fixed point equation, where the g is x comma g of x for all x belongs to I. That means this is the continuous function from I to a comma b which obeys g of xi equal to yi. That means g is a continuous function from I to a comma b which maps all the xi to the yi. G is a continuous function, it passing through the all the given set of data point, therefore this g we can call it as the fractal interpolation function. Now we need to establish this theorem, then one can get the fine fractal interpolation function. Now let us try to prove this theorem. This theorem, for proving this theorem, we need to complete three different parts. First one is we need to show that this graph G is a unique, that means this compact set is the unique compact set. One can understand what is G of G. The G is the mapping x comma G of x such that x belongs to all the I. That means this is the graph of the continuous function which passing through the given set of point. Now we need to prove that this graph is a unique First we need to show the uniqueness of G, the graph of G, so that we give the notation GG, that means the graph of G, so that we are giving this notation, and G of G is the graph of the function we need to prove. Then we need to prove that the function G is continuous. First one, the uniqueness of the compact set, and we need to show that this is the graph of the function G. Then we need to prove the continuity of G. The first part, to prove the uniqueness of this G, let G be the attractor of the IFS. Let G be the attractor of the IFS. Then this one satisfying this equation, right? The G will satisfying the self-referential equation, this equation. That means if you take f of G which is equal to union I belongs to n minus 1, we have n minus number of one mapping, then Wi of G of G. This G must satisfying this equation, therefore we will get this point. Then one can understand, suppose we have one I dash which defined as like this one, that means for all x belongs to I, x comma y for some y belongs to a comma b. That means this G is the unique attractor. Suppose we have one I dash such that, what is this I dash? For some y belongs to a comma b, this x comma y belongs to the set this one. Then one can get, it is clear that f of I equal to I, f of I dash equal to I, because the I is the fixed point of this mapping. Instead of b, if you are taking I, one can get I, because it is the unique attractor. Therefore fi of I, that means the I is the attractor, therefore fi of I equal to also I, because I we are taking from Li. Li is the hyperbolic IFS. How we define the Li of x? Li is a function from x1 to xn to all the subinterval xi plus 1. This is contractive homeomorphism for this iterated functions. This is acting on this I. This I is a compact as well as a complete metric space. This Li is the contractive mapping on I. Therefore this Li on I for all I belongs to n minus 1 will form the iterated function system. Then this iterated function system has a unique attractor, that attractor is I. Now we have taken I dash is the another point which satisfying, we taken like this one, therefore we obtained f of I dash is also I, because if you are taking any point that converges to the attractor I. Therefore one can understand that I and I dash both are same. Now let us move to the second part. G is the graph of the function G from I to a comma b. For proving this one, it is enough to prove that only one y in the interval a comma b correspond to each x belongs to I. So let us take Si is defined as x comma y such that you can take the data point xi for which x equal to xi which map to y, we can take as Si. For all I belongs to n, we have the n number of points. For the n number of points, you can take x equal to xi which is associated with some y. Now we need to prove that we have only one y is corresponding with one x. There is no common point between S1 and Wi of S1 except I equal to 1. It gives that W1 of S1 equal to S1. We arrived S1 equal to x1 comma y1. Since see here there is no common point between S1. So what is S1? S1 is defined as x comma y belongs to g of g such that x equal to x1. And what is wi of s1? For if you are taking I equal to 1, this has the common points, because this wi is a contraction mapping, it will contract the s1. Therefore, there is no common point between s1 and wi of s1 except I equal to 1. So, it gives that if you are taking 1, then it will map to the s1, that means w1 of s1, one can get s1. Then s1 is nothing but x1 comma y1. Since w1 is the contraction of the compact metric space. Now, in the same way, if you are taking Sn, that means here if you are taking instead of x1 you can take xn, here you can take xn, I equal to n, then Sn we can write as xn comma yn. Note that the only point which map to Si are S1 under the mapping Wi and Sn under the mapping Wi plus 1 for all I belongs to n which removing 1 and n. So, here note that the only point which maps to Si are S1 under the mapping Wi. Similarly, Sn under the mapping Wi plus 1 will map to the Si. So, it gives that Si can be written as union of Wi of S1 union Wi plus 1 of Sn. Wi of S1 is x1 and this one is xi. It clarifies that xi has only one image yi for all I belongs to nn. Now, if you are taking 1x, it maps to the only one yi. Now, consider the supremum metric. Now, delta is we are considering as a supremum metric. Delta is defined at maximum of modulus of s minus t such that x map to s as well as the x map to t. That means, we are taking the graph, if you are taking the x here, then x has the two images, like x has the two images s and other images t. Now, what is the delta is maximum of s minus t. For some x belongs to I, we are assuming that this x has two images t and s. S and t is the two images of x. Now, you can find the difference between, you can fix the x, find all the images and difference between all the image you can find and take the maximum, that is delta. Since G is a compact set, so maximum delta is achieved in G because it is the compact, it is a bounded set, therefore, maximum will be attained. Say maximum attaining at x dash of s and x dash of t with delta equal to difference between s and t. But x dash, this x dash, we are taking the x dash, this x dash belongs to I and I plus 1 in the interval for some I. Then there exists a 2 point, Li inverse of x dash and Li inverse of x dash with u and v in G such that S can be written as Fi of Li inverse of x dash of u and T can be written as Fi Li inverse of x dash comma v, because Li is the homeomorphism on I. That means, we are taking here x comma s we have the x comma s and x comma t. For the same x, we have two different images s and t. Here x dash also, here we take maximum of x, maximum among all this we are calling as x dash. Now x dash is belongs to this interval. Then there exists 2 point. What is the 2 point? Li inverse of x comma u, which is equal to s, and similarly Li inverse of x dash comma here x dash and x dash of v, which is mapped to t. Because Li is the contractive homeomorphism, we can find 1:1 correspondence. For yes, we can find such a mapping Fi. That means Fi of this one can get this mapping, and Fi inverse of this one can get t. Now, what is delta? Delta is the modulus of s minus t. So, instead of s, one can apply here this one. For instead of s, one can apply this map, and instead of s, one can apply this one. We know that Fi is contraction with respect to the mapping. Therefore, this can be written as, this mapping can be written as, this is contraction with respect to the second variable Fi. Therefore, q times modulus of u minus v we can write, which is less than or equal to q times delta. Now, delta is less than or equal to q times delta. This, if you are iterating this time, which becomes the q is the less than 1 and greater than or equal to 0. Therefore, the only possibility for q and delta, the q possibility is 0, therefore, the delta becomes 0. It arrives that s and t is not a different element, both are same element. So, if x and t are same element, we already saw that x, if you are taking x, it map to the s and t, then this s and t is the same element, therefore, this x is not mapping to the two different element, they are mapping only one element. So, only one y belongs to a comma b correspond to the x belongs to I. Hence, that means if you are taking one element, it maps to the only one element, then we are taking all these collections. Therefore, the g is the graph of the function g from I to a comma b such that g of xi equal to yi. How arriving g of xi equal to yi? Because we define the function, we define the set si like this one and arriving like this one. Therefore, the function is a graph of the function which maps on I to a comma b such that we will get g of xi equal to yi for all I belongs to in. Then we have to prove that the g is a continuous. For proving that g is the continuous, we can define the map phi from g to g by phi of h equal to fi of Li inverse of x, h composition Li inverse of x, where x belongs to I for all the I belongs to n minus 1 number of points, where g is the set of all continuous function from I to r such that this h maps x1 to y1 and xn to yn. If you are taking x1 and yxn, this x1 must, this is the function from I to r such that this function, the h maps the h of x1 one can get y1 and h of xn one can get yn. The h1 is a mapping from the closed interval x1 comma xn to r. So, finding all such a collection, we put it in G. G is a complete metric space endowed with the uniform metric. If you are taking two function h and h dash, maximum of delta of h and h dash can be defined as maximum of modulus of h of x minus h dash of x. We need to take for all x belongs to I. H is a continuous function on this compact interval, so that it will attain its maximum. So, instead of the supremum we are using the maximum. Then now we will find the distance between image of two function under the mapping phi. So, delta phi of h minus phi dash of h can be written as maximum of phi of h minus phi dash of h. So, phi of h is defined here Fi Li inverse of x comma h composition Li inverse of x. So, instead of Fi Li inverse of x, h composition Li inverse of x. So, instead of h you can take another function h dash. So, Fi Li inverse of x comma h varies from h dash composition Li inverse of x. We know that this function Fi is contraction with respect to the second variable. Therefore, the contraction factor all Ri is less than 1 and greater than or equal to 0. So, one can get Li inverse of x, this Li inverse of x will remove and h composition Li inverse of x minus h dash of Li inverse of x, you can write for all x belongs to I. Now, the maximum among this Ri is does not depends on any, we can take it out. Then what is this one? This is nothing but the distance between the image of h of x and h dash of x. So, if you are taking delta of phi of h minus phi dash of h, that means delta of phi of h minus phi of h dash, we arrived r times delta of, that means distance between h and h dash. Therefore, this phi is a contracted mapping because the r is lies between 0 and 1, 0 and 1. So, it shows that phi is a contraction mapping on G with the contraction factor r. R is the maximum among all the numbers, maximum among all the number we can take as r. Now, phi is a contraction mapping on G and G is a complete metric space. Therefore, this phi has a fixed point. That fixed point, that means the fixed point will satisfy the self referential equation, this one, that means g of x. What is our given equation? Phi of x, phi of h is defined as Fi of Li inverse of x comma g h composition Li inverse of x. The fixed point G, it has the unique fixed point G, we are taking G as the unique fixed point. This is phi is a contraction on G. That means phi of G we can write as Z, phi of G we can write as G, so that this G of x can be write in this form. That means G of x can be write in Fi of Li inverse of x comma G composition Li inverse of x. Now, further the graph of G is an attractor of the iterated function system f and G belongs to G, hence G is continuous. See, the G is a attractor of the iterated function system f and G belongs to Z. What is G? How we define the G? Here you can see G is a continuous function on I. Therefore, G is a continuous function. So, now we proved that G is continuous function, and here we proved that G is a graph of the function from I to a comma b, which satisfying G of xi equal to yi. We already proved this one, and G is the unique set. Therefore, we can conclude that G is a attractor of a continuous function which passing through the given set of data points. This theorem can be summarized as here. See, we have started with the iterated function system here. X, how we define the x? I cross a comma b is our x. This x comma yi is the given set of data point in R power 2 for I equal to 1 to n is given. From this here we can form the set x. X is the complete metric space. Then we defined the Wi is a contraction mapping based on the Li mapping and Fi mapping. Therefore, this set X, that means this complete metric space X together with Wi, we can call it as the iterated function system. Here it is defined as Wi. Then what is the role of this Wi in each of in the X? What is X? X is x1 we are taking here, xn we are taking here. Then A is the minimum among all the yi and B is the maximum among all the yi. Now, without loss of generality, I am taking it as a perfect rectangular region. So, this is my x. What is the role of W1? W1 maps to I1 to A cross B. That means it contract the whole interval to this first interval like this one, and y controls the vertical direction, then here it will map to this one. This is the role of W1, and W2 maps this interval to here. Likewise, Wn minus 1 maps here, so on so on, because I controls in the horizontal direction, Fi controls in the vertical direction. Therefore, that Wi controls both vertical and horizontal direction. So, after applying each W1 we get like the smaller copy of like this one. This is after the first iteration. If we are starting with each iteration, one can get the graph is like this one. By the contraction mapping principle, because Wi is contraction, there exists a unique non-empty compact set Gg such that f of g can be written as g for with this Hutchinson mapping. Then for proving this theorem, what we did, first we use the projection argument, that means uniqueness of the domain I. If there is a one more I dash is existing such that for some y belongs to a comma b, x belongs to I, then the Gg is projection to the x axis. That means since I is a hyperbolic iterated function system, it has an IFS, it has an attractor, that attractor is an I, and here f I dash equal to I and f of I equal to I. Therefore, I is nothing but I dash, both are same. So, hence the graph of G is defined over the whole interval. So, the domain is unique. Then G is the graph of a function interpolation the given data. For proving this one, we defined the set Si such a way that x equal to xi. If you are taking x equal to xi, what are all the y maps to this xi? Initially, we assume that there are many points yi is associated with xi. Then we proved that it is not a many point, all are equal point. So, for that S1 is defined as x1 comma y1, and Sn we arrived as x1 xn comma yn. Then in between 2 and n minus 1, the only point which maps to Si are S1 under the map Wi and Sn under the map Wi plus 1. Therefore, Si can be written as the union of Wi of S1 and Wi plus 1 of Sn. so that we will get xi comma yi, thus xi has a unique image yi. There is no 2 point in G which maps to the only one x, therefore we arrived the uniqueness of the image of xi. Then for only one y correspond to x, if you are taking 2x dash, 1x dash which associated the 2 s and t, then we defined the delta mapping, that means x dash associated the two things. Then by using the inverse of Li, which is contractive homeomorphism, there exists 2 point sit, then it will satisfying this one. Then by using the delta metric, then we arrived that delta is 0 if you are taking 2 s and t, the distance between s and t is 0, therefore we arrived that this t and s is not two different points, this is equals, therefore x dash is mapped to the only one point. Therefore G is the graph of a function G from I to a comma b which passing through the given set of data point are satisfying this equation. Now the continuity of G is proved by defining the map G from H from I to R, where H is the continuous on I and map to the endpoints. Then we proved that we defined the mapping phi from G to G like this one. Then this is the contraction mapping, this has a unique fixed point, that unique fixed point we can call it as G, that G is satisfying the self-referential equation, and the unique fixed point G is continuous, belongs to the G and it is graph of G of the iterated function system. Now this is the data point is given, this is a to b and x1 y1 x2 y2 and xn yn's are given. Hence the continuous function G from I to a comma b with G of xi equal to yi, whose graph is called the fractal interpolation function associated with the data point xi comma yi. So the fixed point obtained from this theorem we can call it as a fractal interpolation function associated with the data point xi comma yi. So next our goal is to find the functional equation of fractal interpolation function G associated with the explicit Li and Fi map, so that we can generate the fractal interpolation function after finding the explicit form of Li and Fi. So one can refer these two books for more details. Thank you.